So heat is the transfer of thermal energy between a system and the surroundings, and that transfer is caused by a difference in temperature. Temperature is a measure of thermal energy. So heat is transfer of thermal energy. Temperature is a measure of thermal energy within a sample. So heat flows from matter with a high temperature to matter with a low temperature until both of the objects reach the same temperature. And we have experienced this in everyday life, right? If you have an insulated container and you put maybe a hot burrito and a frozen, Go-Gurt in there, and then later, a few hours later for lunch, what temperature are those things? They're room temperature, right? They're the same because heat flowed from the hot thing to the cold thing until they were at the same temperature. At the same temperature, we call that thermal equilibrium. Now, that does not mean that there is no more transfer of heat at all, but there's no net transfer of heat. So if something goes one way, it also goes the other way, and there's no change overall. So when a system absorbs heat, its temperature goes up. And we signify that change in temperature as delta T. Again, the delta means final minus initial. The increase in the temperature is directly proportional to how much heat was transferred. And so to make that into an equation, we use a proportionality constant. So up here we're saying that the change in temperature is proportional to the amount of heat. So to make that into an equality, we have to put in a proportionality constant. We're going to call that C, heat capacity. That would have units of joules per degree Celsius, because then the units would come out. So C would be in units of joules per degree Celsius, and then you'd multiply by degrees Celsius, and the Celsius temperatures cancel out, and you have joules, which is a unit of energy. So the heat capacity is the heat required to change the temperature of a system by 1 degree Celsius. So this is moderately useful. Some things have larger heat capacities than other things, meaning it's harder for them to heat up. You have to put more energy into them to get the temperature to change. You get a smaller temperature rise. The heat capacity of an object depends on what the matter is, what substance it is, but it also depends on how much there is. If you think about boiling spaghetti, if you're boiling some hot water, is to make 1 serving of spaghetti. You've got maybe a couple cups of water in a pan, and it's not going to take very long on the stove to get that to boil, right? Starting at room temperature. If you're trying to cook spaghetti for the entire football team, and you've got this giant stock pot with like 15 gallons of water, is it going to take longer for that to boil? Heck yeah. On a big stove in the high school cafeteria kitchen, 45 minutes. I've done that. You don't want to do that. You use the turkey fryer outside, it goes much faster because you can put more heat into it. But the amount of matter matters, right? So heat capacity is an extensive property. It depends on how much stuff there is, and extensive properties aren't all that useful. So specific heat capacity is an intrinsic or an intensive property. It's the intrinsic capacity of a substance to absorb heat. So the heat capacity depends on the amount of stuff. It also depends on the type of material. Specific heat capacity only depends on the type of material. So the specific heat capacity is the amount of heat needed to raise the temperature. Here we're specifying the amount, that's what makes it different, of 1 gram of the substance by 1 degree Celsius. And so the units here are joules per gram times degrees Celsius. Sometimes we talk about a molar heat capacity, and that's the amount of heat needed to raise the temperature of 1 mole of the substance by 1 degree Celsius. Then the units would be joules per mole degree Celsius. And again, units like this are best written as vertical fractions because then your mind recognizes that's a fraction. Sometimes when there's just a slash, your brain overlooks the slash, and then you get into unit problems. So this is joules divided by moles times degrees Celsius. These are intensive properties. They don't depend on how much matter is in the sample. So for specific heat capacity, our equation changes a little, and now we've got Q equals the mass times the specific heat capacity times the temperature change. So that's a nice graphic. It tells what all those things are, but it's kind of hard to see the actual equation. Q equals MC delta T. And sometimes students remember that by saying Q equals MCAT, because the capital delta kind of looks like an A, right? If you just drew this down a little bit, it looks like an A, MCAT. So Q is the amount of heat, the energy, and that's measured in joules. The mass is measured in grams. Specific heat capacity has units of joules per gram degree Celsius, and the temperature change is measured in degrees Celsius. The specific heat capacity is not something that you need to memorize. Here's a table with specific heat capacities of some common substances, and we just go look those up. So we see there's a variety of values here going from like 0.128 all the way up to 4 for water. Here's some, these are not elements or compounds, but glass, granite, and sand. So water can absorb a lot of heat energy without a large increase in the temperature because of its large heat capacity. And going back to this slide, the specific heat capacity of water is 4.18. That's more than 4 times as much as most of the other substances on this table. So to get the same temperature change, you have to put in 4 times as much energy. Or if you put in the same amount of energy, the temperature only goes up by 1/4 as much. So this has a huge influence on our climate because water can absorb a lot of heat energy. And so in coastal areas like San Francisco, where you've got this city on a peninsula and it's literally surrounded by water on three sides, as the sun beats down and the earth absorbs energy from the sun and heats up, because it's hitting so much water, the temperature of the water only goes up a small amount compared to the temperature of asphalt or concrete or even grass. So the bay and the ocean absorb a lot of that heat without changing temperature much. When the sun goes down and stops sending its rays to the earth, then the air cools down, and now heat flows the other direction because the air is cooler, and so the water then releases heat into the air and keeps the air from getting as cold. And so what we see in San Francisco, a high temperature in the summer might be 68 degrees Fahrenheit, right? Which is colder than it is in this room right now. It's 70.5 in here. San Francisco, high in the summer, might be 68 degrees. It just does not get hot very much. High temperature in Fresno, more like 100 on a nice day, right? In August. So water moderates the temperature. It heats up faster and gets hotter in Fresno because we don't have any large bodies of water around to absorb the energy. Water is also commonly used as a coolant because it can absorb a lot of heat without increasing temperature. So in your car engine, you have a radiator with water in it, and the water flows through the hot parts of the engine. It absorbs the heat, but its temperature doesn't go up a lot. And it does get hot, but it doesn't boil and vaporize. And so it comes around and back to the radiator, and the radiator has a lot of surface area, and as the air blows across it, the water releases its energy, its heat into the air, and then it's cooler, and it can go and absorb more heat from your engine. So here's an example using the Q equals MC delta T equation to determine whether a shiny gold-colored rock is actually gold. A chemistry student decides to measure its heat capacity. She first weighs the rock and finds it has a mass of 4.7 grams, and she finds that upon absorption of 57.2 joules of heat, the temperature of the rock rises from 25 degrees Celsius to 57 degrees Celsius. Find the specific heat capacity of the substance composing the rock and determine whether the value is consistent with the rock being pure gold. I read this question and I think, well, there's a much easier way to determine whether this might be gold. How about just find the density? That would be simpler. But that wouldn't illustrate this problem, so yeah. So let's go back and look up the specific heat capacity. The specific heat capacity of gold. Here it is, it's pretty low, same as lead. 0.128 joules per gram degree Celsius. So we're going to need that in our problem, so I'm just going to write it in there right away. So the specific heat capacity is 0.128 joules per gram degree Celsius. Oops. Now that's not something we can use in the calculation, but that's what we're going to compare the specific heat capacity of this rock with. So this is for gold. So I'm going to go through the problem and write down some numbers and see what those mean. And the first number I come to is 4.7 grams. And then I've got 57.2 joules. And I have 25 degrees Celsius and 57 degrees Celsius. So 4.7 grams, that's the mass, right? It even says mass of. I'm going to call that M. And absorption of heat, what letter do we use for heat? Q. And then these two things are temperatures, right? The equation Q equals MC delta T has delta T. Delta T is the final minus the initial. So we need to identify what these are. And here the words tell us. It goes from 25, so that's the initial, to 57, that's the final. So initials 25, finals 57. So this is it, yeah.
Sorry, for future.
Yeah.
So, do we keep the temperature to degrees Celsius or to Kelvin?
That's an excellent question. I hammered into you in chapter 6 that with gases it has to be in Kelvin, right? Here, Celsius or Kelvin is fine. And so it's probably best to just leave it in Celsius. Because the really confusing thing about Celsius and Kelvin is that when you take a difference in temperature, it's the same, whether you're looking at Celsius or Kelvin, because all that's different is the zero. So, yeah, just use Celsius. So we're trying to find the specific heat capacity, so that's this guy right here, C sub S. That means I need to rearrange my equation so that I can get C sub S by itself. So I'm going to divide this side by M, so the M's cancel out. And then I have to divide the other side by M as well. And I'm going to divide this side by delta T, so the delta T's cancel out. And then I have to divide that side by delta T. So I end up with the specific heat capacity is equal to Q, the heat, divided by the mass, times the change in temperature. So Q is 57.2 joules, and the mass is 4.7 grams, but I wasn't specifically given delta T. I'm going to have to calculate that. Delta T is the final minus the initial. So the final's 57, the initial's 25, and I think that's 32 degrees Celsius. So I've got 32 degrees Celsius down here. If we look at the units on the specific heat capacity, we've got joules and grams and degrees Celsius. And over here in our equation, we've got joules and grams and degrees Celsius. Most of these problems are not going to present you with icky unit conversions. Okay, usually they'll be pretty close to what you need, so you don't have to worry about that as much. The gas laws, we like to really mess with you on the units. So if we get out our calculators and do this problem, we have two numbers in the denominator, so you need to be careful with that. 57.2 divided by 4.7 divided by 32. Oh, pressed the wrong button. Let's try that again. So that looks like it would have two significant figures, and I'm looking for a ballpark anyway. So 0.38 joules per gram degrees Celsius. If you got a significantly larger number, you are miscommunicating with your calculator. So it says find the specific heat capacity, so I found that. There's two things though, there's two answers here. Determine whether the value is consistent with the rock being pure gold. Is this rock gold? Does this 0.38 match up with 0.128? No, not even close. So the other answer is no. If it did come out to be 0.128, does that prove that it's gold? No, because lead has the same specific heat capacity as gold. But it would be consistent with the rock being gold. This is not consistent, so it demonstrates that the rock is not gold. Any questions?
You said, so Q is equal to, that's just heat?
Q is heat.
Right.
Yep, which is a form of energy, a transfer of energy. Yep.
Heat capacity is
Heat capacity is an intensive property, well, specific heat capacity. I told you about heat capacity. We almost never use it. So it was just kind of specific heat capacity from now on. Is how easy or how hard is it to get the temperature of this thing to rise? So if you think about going to like a steakhouse and you get this plate of food and you've got a steak and you've got a baked potato and you've got a couple pieces of Texas toast, right? Do they still do Texas toast or really fat toast? So it's all hot when it comes out. Which one of those foods cools down the fastest? The toast, right? Which one of those foods has the least amount of water in it? The toast. Which one stays hot forever? The baked potato, right? Baked potato has a lot of water in it. And so it can lose a lot of heat without changing temperature very much. And so it takes a lot longer for the potato to cool down. So I bet you didn't know there was chemistry in eating a steak dinner. 0.38 and no. Here's another example. A 55-gram aluminum block initially at 27.5 degrees Celsius absorbs 725 joules of heat. What is the final temperature of the aluminum? Well, again, let's pull the numbers out and write them down. 55.0 grams. I've got 27.5 degrees Celsius and 725 joules. And I need to label these things. Since we're talking about heat capacity, I'm probably going to be using Q equals MC delta T. So that can help me with what letters I might want to use. So 55 grams, that's the mass. So we'll call that M. 27.5 is a temperature. It's on delta T though. Is that the initial temperature, the final temperature? It's initially at, they even use the word initial. So this is the initial temperature. And then absorbs 725 joules of heat. Heat is Q. You may want it to be H, but it's Q. And then I'm trying to find T final. So this is the equation I have available. It doesn't have T final sitting in it. But what's delta T? The final temperature minus the initial temperature. Oh, I have the initial temperature. So if I find delta T, then I can find the final temperature. So from this equation, I'm going to find delta T. So I need to rearrange, divide by M, divide by M. These M's cancel out. Divide by the specific heat capacity, divide by the specific heat capacity. So the change in temperature is Q divided by the mass times the specific heat capacity. So I've got Q, 725 joules. I've got the mass. Oh, I have to go look it up. So on an exam, the specific heat capacity would either be given in the problem or on the table, periodic table page. But in the homework, you're just going to have to go look it up. And they're not going to say, go look it up. They're just going to assume that you can figure that out. So we have a missing piece. We need to go look it up. And, you know, if you don't have the table from your textbook handy, you could use Google. In fact, let's ask Siri. Hey Siri, what's the specific heat capacity of aluminum?
The specific heat at STP of aluminum is 904 joules per kilogram Kelvin difference.
Okay, so that's different units. Not so helpful. So you might have to look around a little bit. I'm not going to take the time to look around because I can just go back a couple slides. And aluminum is 0.903 joules per gram degree Celsius. So specific heat capacity, I'm going to stick it up at the top. 0.903 joules per gram degrees Celsius. That is definitely related to the number that Siri gave me, but she was giving me SI base units, which is not what we typically use in chemistry. Okay, so I'm going to put that number down here, 0.903 joules divided by grams times degrees Celsius. In the previous example where we were calculating the specific heat capacity, none of the units canceled out. But here, some of the units are going to cancel out. So the grams are going to cancel, and the joules are going to cancel, and my units end up being 1 over degrees Celsius. So when I do the math here, 725 divided by 55 divided by 0.903. And 3 sig figs, 14.597 degrees Celsius. Is that the final temperature? No, that's the change in the temperature. So I've got my equation down here. The change in temperature is the final minus the initial. So the final temperature is equal to the change in temperature plus the initial temperature. So So 14.597 plus 27.5. .097 degrees Celsius. I would round that to 43.0 degrees Celsius. Any questions?
Why is it 43 degrees Celsius instead of 42.1?
Because I was dumb. Yeah. It should be 42.1. I don't know. I was trying to see if you're paying attention. No, I was just being stupid. Thank you for catching that. 42.1. Yeah. Any other questions? And the answer is, come on, 42.1. So when we have two objects at different temperatures and we put them in contact with each other, like the example of the, what was it, a burrito? Hot burrito and a frozen Go-Gurt. Sorry, this is just a little personal story of a dumb thing one of my kids' friends said. So kid's over to play, and he's like 12 or 13. And so I asked the kids, hey, do you want a frozen burrito for lunch? He's like, nah. And then when he finds out I was going to heat them up, he wanted one. I'm not going to give you one that's still frozen. I little dance that one. Not my kid. So we've got two things at different temperatures. The heat flows until they get to the same temperature. We call that thermal equilibrium. The amount of heat that's lost by the hot object is equal to the amount of heat gained by the cold object, because conservation of energy. We can't have energy just being created or destroyed. So the amount of heat being transferred from one to the other is the same. And so we can define one substance as the system and the other as the surroundings. And then we're kind of getting to stuff we talked about last week. So we can quantify the heat exchange in this way. Q for the system is equal to Q for the surroundings, but the sign is opposite. Just like a money transaction, the amount of money I give you is equal to the amount of money that you receive, but it's positive for you and negative for me. So these two things are equal in value, but opposite in sign. So here we have a block of metal at 55 degrees Celsius, so that's warm, and we put it into a beaker of water that's at room temperature, 25 degrees Celsius. So the hot metal transfers energy to the cold water. And we can figure out what the temperature change is by looking at the mass of the metal and the mass of the water and the specific heat capacities of the two substances. So we're defining the metal as the system and the water as the surroundings. We're going to ignore anything that might happen outside the beaker. So the Q for the metal is equal to Q for the water, but opposite sign. And so we can calculate each of those things separately. When we stick it into this whole equation here together, it kind of gets confusing. But Q equals MC delta T, right? So Q for the metal is going to be the mass of the metal times the specific heat capacity of the metal times the change in temperature for the metal. So here for Q metal, I just substituted the rest of the equation. Over here for Q water, if we just ignore this minus sign for a minute, just cover that up. Q water is the mass, the specific heat capacity, and the change in temperature of the water. And when I put these equal, I stick a negative in front of one side because it's going from one thing into another. It's just multiplying by -1. Any questions? The train wants to know something, but I don't speak train, so have to ask somewhere else. Sorry. So we could calculate a lot of different things depending on what we know. So one of the things that we can calculate is, well, if I know the initial temperature of the metal, and I know the initial temperature of the water, and I know the masses of each and their specific heat capacities, I could calculate the final temperature of the water. It's kind of a messy calculation, but I can do it. So here's an example that's not as messy. A block of copper of unknown mass has an initial temperature of 65.4 degrees Celsius. The copper is immersed in a beaker containing 95.7 grams of water at 22.7 degrees Celsius. When the two substances reach thermal equilibrium, the final temperature is 24.2 degrees Celsius. What is the mass of the copper block? Why don't you just stick it on a balance, right? Because then we couldn't do this calculation that illustrates what we're trying to learn. So this is the kind of problem that it might be helpful to draw a picture. It's actually never wrong to draw a picture illustrating the problem, just don't spend too much time making it beautiful. But sometimes it's more necessary than others. And so this is a situation where I think it's really helpful. So here's the beaker. And it's got water in it. Water's blue, so make this blue. What do we know about the water? Do we know the mass? We know 95.7 grams of water. So the mass of the water is 95.7 grams. At 22.7 degrees Celsius, well, that's obviously a temperature. Is that an initial temperature or a final temperature? It must be the initial, because then in the next line it says the final temperature for each thing is 24. So this is the initial temperature. And the final temperature is 24.2 degrees Celsius. So I've got a copper block. So there's my copper block. I'll make it kind of copper colored. It's in the water. What do we know about the copper block? Initial temperature is 65.4 degrees Celsius. What's the final temperature? 24.2. When we have a hot thing and a cold thing, and we let them transfer heat, if we wait long enough, they will be at the same temperature. So both of these things have the same final temperature. They had different initial temperatures. Well, those were all the numbers that I was given in the problem. So what we have here is we have Q for the metal, and I'm going to use a subscript here just to be clear. Q for the metal is equal to Q for the water, but there's a negative sign. Now I can put the negative sign on the right side, I can put the negative sign on the left side. It's not saying that Q for the water is negative, it's just saying that these two quantities are opposite in sign. So I'm trying to find the mass of the copper block. Let's maybe make a note of that down here. Mass equals question mark. And then I'm missing some information. Because Q equals what? Our equation? Q equals MC delta T. So I've got information about mass and temperature, but I don't have specific heat capacities. I need those, so I have to go look them up. So back to our table. Our friend table 7.4. So for water, it's 4.18, and for copper, it's 0.385. So specific heat capacity for the copper, 0.385 joules per gram degree Celsius. And for the water, is 4.18 joules per gram degree Celsius. Can I calculate Q for the water? To calculate Q, I need M, C, and delta T. I have all those things, right? So Q water is MC delta T. The mass is 95.7 grams. The specific heat capacity I looked up, it's 4.18 joules per gram degree Celsius. Got a little messy. And the change in temperature. Well, delta T is the final temperature minus the initial temperature. The final temperature is 24.2. The initial is 22.7. Don't want to try that in my head on a Monday. 1.5. So this is 1.5 degrees Celsius. So I multiply those things. Oops. And I find that Q for the water is equal to, my calculator is saying 600.039. The grams cancel, the degrees Celsius cancel, and this is joules. Because of that small change in temperature, I only have two significant figures, so that would be this one right here. What I'm trying to find is the mass of the copper block. I found Q for the water. I have this relationship between Q for the water and Q for the copper. So I have Q for the water, and this is negative Q for the water. Well, what if I multiply both sides by -1? This -1 times -1 becomes positive, right? And the other side becomes negative. So if Q water is 600 joules, then Q for the copper is negative 600 joules. And then we can stop and ask ourselves, well, do those signs make sense? A change in temperature where it goes up, like the water heated up, that means that energy came in, so Q is positive. For the metal block, it got colder by losing energy, so Q is negative. So Q for the Copper is that number which equals the mass of the block times the specific heat capacity times the change in temperature. And so if I want the mass, I can divide by specific heat capacity and change in temperature. To find out what M is. So I've got negative 600.039 joules divided by, yeah, I screwed up. See over here? I divided by mass. I don't know why I did that. I want the specific heat capacity in there. That's better. And there is just not enough room down here, so I'm going to go somewhere else. I'm going to go up to the top. We don't really need that title. Or this thing over here. Because I can't just go to another screen. Okay, so M for the metal is Q divided by specific heat capacity times delta T. And we've already identified that the Q is minus 600.039 joules. So divided by the specific heat capacity and the change in temperature. So the specific heat capacity we looked up, it's 0.385 joules per gram degrees Celsius. And then we need the change in temperature. It's kind of a mess, sorry. The change in temperature is the final minus the initial. The final is 24.2. The initial was 65.4. 24.2 minus 65.4, negative 41.2. Is it okay that it's negative? Yeah. When the temperature of one thing goes up, the temperature of the other thing has to go down. And so one change in temperature is positive, one change in temperature is negative. One Q is positive and one Q is negative. The mass and the specific heat capacity are always positive. So I'm going to plug delta T in up here. I've got negative 41.2 degrees Celsius. I check my units. Joules cancel, degrees Celsius cancel. I end up with grams. So I've got negative 600.039 divided by 0.385 divided by negative 41.2. And this should have two significant figures. So let's get around to 38 grams. Any questions? Yes. Pardon me?
So the heats are always going to be the same, but one is going to be losing?
Yes. Yeah, we've got the system and the surroundings. And so one is gaining, one's losing. The temperature changes are not the same because the masses and the specific heat capacities are not the same, but the amount of energy transferred is the same. Sorry, I'm lost here. Ooh, 37.8. The book has the wrong number of sig figs. So we talked about the change in internal energy is equal to Q plus W, heat plus work. So one type of work is called pressure volume work. This occurs when a force caused by a change in volume acts against an external pressure. So in our illustration here, we have a cylinder with a gas, and the gas expands in volume. And that causes the piston to move. There's an external pressure, which is probably at least atmospheric pressure, that it has to push against, and so that's work. When gases expand, the change in volume is positive, but the system is doing work on the surroundings, so W should be negative. So pressure volume work is defined as W is equal to negative P delta V. The P there is the external pressure that the gas is expanding against. And then we have this very useful relationship here. 101.3 joules is equal to 1 atmosphere times liter. Which at first that seems kind of weird, but then when you look at this equation, we have a pressure, atmospheres, times a change in volume, could be measured in liters, and that is equal to work, which is a form of energy, right? It's a transfer of energy, and so the unit joule works out. We don't have to worry about why it is, it just is. This is the sort of work that's happening inside of an internal combustion engine. The combustion occurs inside this cylinder, and when it combusts, it produces gas, and it gases, and it expands, and it pushes down on this piston. And you've got the coordinated exploding in multiple cylinders, and you can translate that work into the forward movement of your car. So a cylinder equipped with a piston expands against an external pressure of 1.58 atmospheres. If the initial volume is 0.485 liters and the final volume is 1.245 liters, how much work in joules is done? Well, we've got 1.58 atmospheres, ATM, and we've got 0.485 liters, and we have 1.245 liters. This is the external pressure. It says that. This is the initial volume, and this is the final volume. It's asking how much work is done. Well, we just learned that work is equal to negative external pressure times the change in volume. We have to calculate the change in volume. That delta means you take the final value minus the initial value. .245 minus 0.485. So delta V equals 0.76 liters. So the work is equal to -1 times the external pressure, 1.58 atmospheres, times the change in temperature, 0.76 liters. And when I do the math, I get negative 1.2008. Should have, I was sloppy over here. When subtracting these, they both had 3 decimal places, and so this is actually 0.760 liters, which affects the number of sig figs in the answer. Negative 1.2008, 3 sig figs. And what's the unit? It's not joules. It's atmosphere liters, right? The atmosphere times liter. They don't cancel out. You can't magically turn them into joules. You have to use a conversion factor. .3 joules is equal to 1 atmosphere liter. That number 101.3, is that at all familiar? Pascals. Yeah. So I take my negative 1.2008 and multiply by 101.3, and I get negative 121.64 joules, or negative 122 joules.
So you can say that 1 joule is equal to 1 kilopascal. Approximately.
No. Because the relationship between joules and pascals is different. The pascal is related to the atmosphere liter.
Which is
So an atmosphere liter is a kilopascal. So I come up with work equals negative 122. If I'm doing this on Mastering Chemistry and I type in negative 122, it's probably going to complain. Because what is the question asking? How much work is done? Like, how much money is spent? Minus $500. Do I need the minus? No, because spent, right, tells. So work being done, it's probably going to ask for just 122. So 122 joules of work is done by the gas. You can be really specific if you want to. I don't want to be misunderstood.
So would it be basically similar to absolute value?
It would be similar to absolute value. And what gets really tricky is that sometimes you need the negative sign and sometimes you don't. But it's like money. If I talk about spending money, I don't say negative $5. But if I look at my bank account, there's positive numbers and negative numbers. Because there's no words there, and I need to know the direction. Was money coming in or out, right? So we deal with it with money. It just gets a little confusing with the energy. So let's see what the book says for the answer. Oh, it says minus 122. Here's another one. When fuel is burned in a cylinder equipped with a piston, the volume expands from 0.255 liters to 1.45 liters against an external pressure of 1.02 atmospheres. In addition, 875 joules is emitted as heat. What is delta E for the burning of the fuel? These are the sorts of calculations that engineers are interested in. So the volume expands from 0.255 liters, so that's initial volume, to 1.45 liters, that's the final volume. And the external pressure, P external, is 1.02 atmospheres. and then it says 875 joules is emitted as heat, so that's Q. Q is going to be positive or negative? We're looking at the fuel, right, and it's emitting, it's losing energy, and so we need to specify that Q is negative 875. They want to know what delta E is, and so we have to go back to last week and remember that delta E is equal to Q plus W. The heat transferred plus the work done equals the change in energy. So the heat exchanged is minus 875 joules plus W. I have to calculate W. W equals negative external pressure times delta V. Well, delta V is the difference of these two guys. So 145 minus 0.255. 1.45 minus 0.255. So 1.195 liters. Negative times the external pressure, 1.02 atmospheres. Change in volume, 1.195 liters. And so I can multiply those. And I get negative 1.2189 atmosphere liters. Or liter atmospheres. Can I add joules and liter atmospheres? No. They have to be the same unit to add. So I need to convert this to joules. So the work is equal to negative 1.289 times 101.3, negative 123.47, lost track of my sig figs, 3 sig figs, joules. And we can double check our sign there. The volume expands against an external pressure, so the gas is doing work on the surroundings, so W should be negative, and it is. So don't overthink this. Let your calculator do that for you. Minus 875. Plus negative 123.47. This equals minus 998.47. Minus 998 joules. So that's delta E, the change in internal energy when this sample of fuel burns. Any questions? Minus 998.